you all for inviting me to this seminar series. Glad to be here. So I was going to tell you some things about primarily inspired by holography, investigations of spectral functions and their asymptotic behavior at higher frequencies. I will largely talk about the behavior in cases where I can control this using the holographic dual. But I will say some things which I think are quite general and suggestive that we could probably just see by bootstrap in OPE. So I'll motivate it from the OPE standpoint. I'll switch to the holographic side and then stay in the holographic side for the later part of the talk. So I'll start with the brief motivation, which this audience has no real need for. Most of you have been thinking about very related things for a long time. I'll say a few things about thermal OP and why I think the spectral function is a nice object, and argue that there is, in a particular regime, in fact, I'll argue something that's slightly more general than what we said in our paper from a few months ago, that the spectral function of conformal primaries with integer scaling dimensions actually shows a very nice factorization. So you can isolate the OPE part from in this factorization channel from the non-perturbative data explicitly. And then I will motivate a separate study of the non-perturbative data, which will involve excursion into WKB techniques. WKB techniques are more or less the standard WKB techniques that we are used to from quantum mechanics, except that I'll dress them up a little bit more to actually gather a full transseries, not leading WKB that we typically tend to do Bohr-Sommerfeld type analysis. Okay, and then I'll end with some comments on what this has to do with the black hole singularity, which was sort of my main motivation for getting into this discussion. Okay, so let's start with some comments about the why we care. And the goal for me is to basically look for observables that are good probes of emergent geometry in holographic systems. Okay. Now, of course, ideally, what we would like to do in reality is to basically start with a quantum field theory, which supposedly has holographic dual, compute in the quantum field theory, and then argue that whatever we are computing has some geometric avatar in the dual space-time that has some incarnation in terms of the field theory data. Of course, we are far from this because we don't know how to solve strongly coupled even planar gauge theories. But what we can do is, as a precursor, at least infer where to look by looking at observables computed from the geometric side. And historically, this has been very successful, and many people have contributed to this endeavor for the last, I would say, nearly 3 decades now. The goal has always been to either pick up simple observables in the quantum field theory, maybe correlation functions or gauge invariant operators, or in more recent era, think about things like entanglement entropy of subregions, et cetera, and use these as diagnostics of geometric features in the bulk, be they causal properties of the bulk, be they horizons, be they singularities, et cetera. So the goal, which I'll come to by and by, is in this talk, I'm interested in asking a simple question, which was motivated by work of Witkowski, Hubeni, Schenker, and Kleban about more than 2 decades ago. Namely, they said, if we studied thermal 2-point functions in conformal field theories, then those thermal 2-point functions in a particular regime should be sensitive to the fact that the dual bulk geometry in the planar large N strong clapping limit is a black hole with a curvature singularity. And the curvature singularity can be encoded in a certain divergence or a bouncing singularity, as it's now being called, of this thermal 2-point function. Okay, so that's where we're going to go, but I'm not going to go there just yet. But that's sort of the anchor point for this discussion. So to get there, let me start with something that you folks are all familiar with, and by starting about looking at thermal 2-point functions. In some CFT in these space-time dimensions. Okay, and I will start in Euclidean and then pass to Lorentzian. And what I will assume, I'll make some assumptions, which are not always true, but certainly will suffice for what I want to say. I will assume that the thermal state, the thermal density matrix, is canonical. Namely, I'm not turning on any charges for this discussion, but we can do that. Much of what I'm going to say won't change. And gauge invariant operators, which I will consider, where delta is the conformal dimension satisfying unitarity bound. I will only look at scalar operators. Everything I say, I believe, can and does extend to spinning operators, but I also won't discuss them. Will be these gauge invariant operators will be assumed to have no 1-point function. Okay, so this is not always true in thermal field theories, and the CFT will be on Minkowski space. So if I'm Euclidean, RD minus 1 cross S1, beta. Okay, so as you folks know, that you can scalar operators can pick up a wave in the thermal state. I'm just going to assume by translation invariance in this case, nothing else picks up a wave. We can generalize the discussion when it does, but this will simplify my life for this purpose. Then I will use the fact that the scalar OPE, the OPE of O delta itself will contain double traces. And always, because I only turned on the canonical density operator, the stress tensor and its multitraces and its multiples. Okay. So this is the sort of restricted OPE I will work with for this discussion. We can talk about more what could happen more generally. And if you then try to write out take the OPE in Euclidean space, say in coordinates, what do I want to call them? Let me call them the Euclidean time TE and spatial coordinate X. This converges in the region okay, so it converges in the disk of size beta, the thermal disk. Okay. So I will start with this Euclidean OPE, which I will assume basically gets contributions only from the double traces and from the stress tensor. And then what I'm going to try to do is consider its Lorentzian counterpart by computing the commutator of the operators, one inserted, let's say, at 0, and the other at Tx. And this is the commutator expectation value at finite temperature. Let me call this function g of Tx. So the OPE, the Euclidean OPE has singularities along the light cone. when t squared plus x squared hits the light cone, and is at the light cone originating from the origin. And so what this computes is that this guy is the discontinuity of the Euclidean object, corresponding Euclidean object across that light cone. So I'll just put E whenever I want to mean the Euclidean object. Question. And we can write down what this is. So this is this guy. And from this, so this will have some OPE like expansion, where I will get contributions from, in general, one structure constants times 1-point functions, or in this case, that's double traces, and the discontinuity piece of the Euclidean thermal Green's function with contributions from intermediate operators and their spins. And this gadget can be controlled completely from Euclidean OP. Great. Now, from this Lorentzian commutator, we can pass to something something slightly more physical and interesting, namely the spectral function.
Can I ask something here already?
Of course, please.
It's not always clear that one can commute infinite sum of operators in a discontinuity. Can you quantify the effect of doing this?
Yes. So that's a great question, and as far as I know, the full story for how much the OPE controls the analytic continuation in general quantum field theories for correlation functions is not fully resolved. In this case, I think the main singularities are the light cone cuts. So I believe in this case, although I don't have a proof, it's possible to probably make it rigorous for the 2-point function and show that this operation is meaningful. The case where I think I can make a sharp statement is 2D CFTs. Please go ahead.
No, go.
Yeah, in 2D CFTs, you can make a sharp statement because the OPE converges in a much bigger domain than its natural domain of convergence by passing to elliptic coordinates. But I don't think that's true in higher dimensions. I mean, what you will see post facto is that there are some lessons we will extract from this OPE analysis, and then post facto verify them from the, say, holographic computation where I'm not using the OPE per se. And the fact that they work suggests to me that there is sort of much better behavior than you would have expected.
Yeah.
Please just feel free to interrupt me anytime. I don't have an agenda of how much I want to say, but I'm not going to pay attention to. So don't put up your hand because I won't be paying attention to the thing. Just unmute yourself and ask. Good. So one can say some things about the spectral function, and I want to say something about the spectral function from this analysis. So let's take this analysis which is in position space, and just piecewise Fourier transform. Okay, so let's pass into Fourier domain. Let me make sure I'm in the same page. And I want to be here for reasons that will become clear later. Okay? And I claim that by just manipulating the OPE expressions, you can derive the following formula in the Fourier domain, which is interesting and which has been sort of understood by various people. That there's a theta function on the light cone. There is a sort of conformal factor, which is a power law. There is this double traces plus multi-stress tensors contribution from the OP. Now, a priori, I'll say something about this in a second, plus exponentially small corrections. I put beta omega because the scale is set by temperature. There's no other scale in the problem. Okay. Now, there's some very simple kinematic accidents which sort of justify what I just said, but they don't fully make it precise. If you look, so in position space, when you did the expansion in the OP, there were some position space polynomials from the Gegenbauers, et cetera, and the Fourier transform of them produces some stupid zeros. Okay, so the zeros of the spectral function block it has zeros at the following locations. When the intermediate operator differs from the exchanged operators, intermediate operator twist differs from the exchanged operator's dimension by integers. Okay, so the double twists do not contribute to this expression. Okay, so only thing that contribute when this condition is satisfied is the multi-twist. Okay, so I'll leave my expression in general and say the double twist contribution vanishes when this condition is satisfied. There's a second set of zeros, which is also kinematical. Which has the following interpretation. It says that if you now let's make the following assumption. Let's say that the scaling dimension of the operator is integers. Okay, so greater than unit algebra. I'll just put. Then, when you hit these integer conformal dimensions of your probe operator, whose 2-point function you're computing, you get no contribution from the double twist. You also don't get any contribution from these from some multi-stress tensors after a certain point. Okay, and this you can verify in the holographic context. And I will just say the statement. By just staring at, which I will spell out a little bit more in detail, the spectral function in the holographic context has the same prefactors. And then, but then it only has contribution from a certain number of stress tensor contributions. And then there's this exponentially small terms. So in some sense, it says that in this holographic setups, assuming that there were no 1-point functions. Sorry, this is me. What happened here now?
Yeah, like okay, now
Okay, it's
it's
back.
good.
Yeah. Assuming there are no 1-point functions for other operators, the only thing that shows up in the spectral function is a finite number of multi-stress tensors. This is quite remarkable because everything which is not in this finite number of multi-stress tensors is non-perturbate. Okay. Now you can check this, and I will check this in various different ways, but one easy check you can do is you can just write down the answer for 2D CFTs, and in 2D CFTs you would see that this is immediate. Okay. Then the 2D CFT, the main contribution comes only from multi-stress tensors from just the Virasoroji descendants, but nevertheless, this statement at integer dimensions is very easy to see. Okay, so I will use this as a motivation to study operators whose dimensions are integers. Okay, and say something about their spectral function. The later part of the talk will not really specialize to integer dimensions, although I will use the spectral function data that I already extracted to say something about the asymptotics. Okay, is this part clear? I'm happy to take questions about this part before I proceed to something slightly different. Great. So just to recap, we've basically argued ourselves into a position of saying it is interesting to consider the spectral function for operators whose dimensions are integral. And now let's see what we can learn about such operators from holography. Okay. And here I'm going to say something first very general about thermal 2-point functions, building on work done initially by Bonelli, Tanzini, and friends, Bonelli, Tanzini, Iosa, and Painalichtig, who derived an interesting connection formula for wave equations satisfied by fields in asymptotically ADS black hole spacetimes. Okay, so I won't derive all the technology. I'll just use that to tell you something about the thermal 2-point function. Okay. So we have our operator O delta, and it's dual to some field phi, scalar field in ADS. And we will look at the Klein dynamics of phi delta in a Schwarzschild ADS d+1 background. Okay, we can all write down the wave equation. I will just write down the wave equation in a particular form. I'll say that in some coordinates, I can bring this wave equation to some Schrodinger-like form. With some potential t. Okay. Now, this potential turns out to be meromorphic with singularities at the boundary, which I'll take to be at 0. I'll take the horizon to be at unit radius, but there will be various complex images of the horizon in this background. So if I'm in d dimensions, d plus 1 dimensional ADS, a Schwarzschild, I will have these many zeros, d over 2 minus d over 2 zeros. And then there is another singularity, a black hole singularity, which in these coordinates is at z is equal to infinity. So there are basically d plus 2 singular points. D over 2 plus 2 singular points.
Mukund, I don't know if it's only me, but the right
Is
edge
not
of
visible?
your screen is a little bit outside of the... Exactly, now it's fine.
No, that's fine.
Yeah, thank you.
Sure. Now, the singularities are easy to interpret. At every one of the horizon, the wave function basically phase rotates. It has a monodromy by e to the beta omega, where that beta will get dressed by this phase factor. Okay? So at the physical horizon, it will just be e to the beta omega. It will give you a Boltzmann factor. But at the complex horizon, the Boltzmann factor will be phase dressed by these complex phases. At the boundary, you will basically pick up the conformal dimension. That's the residue of the singularity. And at the black hole singularity, there's some number which depends on which is not interesting, but we'll come back to that later. Okay. I will also use dimensionless units. So let me just write W to be beta omega over 2 pi, and Q to be beta K over 2 pi. Now, this result from what goes by the name of the three-step formula can be interpreted as follows. So let's first write a formula and then explain. So let me start by writing the formula for the retarded Green's function as a function of W and Q. I claim this is given by some number, which depends only on the conformal dimension. It doesn't depend on the frequency. And there is some function, which I will explain later what it is, which is a function of omega and Q, and maybe the conformal dimension. But otherwise, the rest of the function is actually quite simple. Let me write this and then say what I mean by here. In fact, for once, I will write it explicitly with beta omegas. Where nu is delta minus d over 2, which is what I will continue to use henceforth. Okay, so clearly nu and nu is non-negative integer. Okay, so this guy, so the gamma functions are explicit. What I need to explain to you is sigma and what is W. So the way to think about this is the following. So this Schrodinger equation, because it's a meromorphic equation, it can be interpreted, for what it's worth, as the BPZ equation in an auxiliary two-dimensional CFT. Okay, it's not a physical CFT that I'm using. I'm going to use some data about some semi-classical 2D CFT. Basic, think of it as Liouville CFT in the large central charge limit. Then I can interpret the solution to this differential equation as the following, as computing an appropriate semi-classical Virasoro block, which I'm going to use to write down what sigma and W are. So imagine you do the following in a 2D CFT. You insert Liouville operators with some conformal dimensions fixed by the residue of these singularities at the boundary, and then at the horizon, the physical horizon. And then you keep going in this comb channel across all these complex horizons until you get to the singularity. Now, in this auxiliary 2D CFT calculation, the Liouville weights or the conformal dimensions of operators inserted at these ends are fixed. So here it's fixed by the conformal weight of the operator. Here it's fixed by IW. Here it's fixed by some number. And everywhere else, the conformal weights are fixed by W with some phase factors. Okay. But as I fuse these two operators, some other operator runs in this channel, and its momentum is this parameter sigma that I defined here. Okay. So if you can solve this fusion problem into the CFT for this D over 2 plus 2 dimensional correlator, then that conformal block in its semi-classical limit determines W, but it also knows about sigma because sigma is related to W by some derivative relation. Okay. I will not use that fact, but this is sort of the one way of saying how to write down this formula and how to interpret it. Okay. But I will use something else, namely the following. So from the point of view of the Schrodinger equation, these 2 points are singularities. So if I encircle these 2 points by a curve and compute the monodromy as I go along the curve, by which I mean the following. So take trace of the monodromy at the horizon, which is set by the scaling weights, omega, the transport from horizon to boundary, and then the monodromy at the boundary, and then transport back from boundary to horizon, which is this closed curve. This guy is is up to a factor of 2 cosine 2 pi sigma. So sigma is really physical. It's basically from the point of view of the wave function. You take a wave function which is in this 2-dimensional. It's a second-order linear differential equation. It has two linear independent solutions. If you take a solution basis at one point and go around this curve that I've drawn C here and ask how much I have phase rotated, that's this matrix. I compute the trace of that matrix, and that's cosine 2 pi sigma up to some factor of -2. Okay. Now, some nice fun things with this formula. Namely, from my Green's function, I can, of course, write down what the spectral function is. This guy is up to some number. Still some product of gamma functions. All I did was use some gamma function identities to simplify this. But if you specialize to integer dimensions, then this formula becomes even nicer. I claim you get a polynomial of degree 2 nu from this gamma function. The arguments of the polynomial are this W and sigma. And then which I'll block off. And then some very simple factors. Namely, up to some polynomial factor on this conformal block. The remainder is pure exponential, coming completely from Boltzmann type factors and this monodrome. I will now make a striking claim, which we can prove now, that this guy it basically reduces to the OPE data. And this guy is the non-perturbative piece that's not accessible to the OPE data. Okay, so I would like you to imagine this in the following sense. You're trying to compute the spectral function in a Taylor series in omega and q. There's some leading identity contribution, whose power law is fixed by the dimension of the operator you're talking about. Then there are corrections. Of course, because we are in frequency space, we don't get corrections from double traces. We assume that no one-point function is turned on. So we get contributions from a finite number of stress tensor multiples. But that series truncates. So it's like you're doing some kind of loop expansion of some QFT object. That loop expansion truncates, but underneath the truncation, there's an exponential incident on correction. Okay. Now, we're not done because I still have given you some interpretation of what sigma was or what cosine 2 pi sigma is. Cosine 2 pi sigma is the monodromy. If I can control the second piece, I can control completely the non-perturbative physics.
Can I ask a question?
Yes.
The polynomial block seems to depend on sigma as well, but then when you write it down, when you spell it down,
yes,
I don't see sigma anymore.
That's correct. So,
okay.
Very good. So indeed, so this is a piece of magic. We don't know how to prove this in general. What we did do was do the following. We were able to check by using homological recursion that in the limit we're interested in for the blocks we were interested in, at the integer dimensions, this combination is exactly this power law. By solving for sigma and plugging in and checking. So we have strong numerical evidence that it works. I think I have a separate argument now for the fact that it has to be the power law. The identity contribution has to work out correctly, which already is buried with this polynomial and sigma. This polynomial is not of the right degree. Which would take me some time to explain, but let me tell you quickly how we worked it out. We worked it out by arguing that when the dimension is integers, as you very well know, the OPE has logarithmic terms. From the holographic side, this means that the expansion near the boundary here, there are logs in the solution. By basically playing around with the monodromy in that log limit, we were able to show the thing actually just factorizes. It's some finite line calculation that just pops out of the result.
I see.
So you can do this without going through my formula for the blocks, but independently, and therefore it implies that this product must be power law, independent of sigma.
But then, like, since sigma seems to be tied only to the non-perturbative piece, like, do you have any idea of what the sigma represents from the CFT point of view? Maybe you're going to talk about it, but
not particularly. I mean, for me, many things. Well, okay. Let me say something philosophical, and then we be more practical. From a CFT point of view, the bulk wave equation is already mysterious. Right? I mean, the CFT correlator was supposed to be some object. The fact that it can be obtained by solving a differential equation and taking some connection coefficient ratio, this is already some miracle of ADS CFT. It's not some pre-given statement about CFTs. So sigma is some feature associated with the differential operator. So it is not obvious how to immediately connect it to some CFT data. But
Yeah.
it is true that from the holographic side, there's something to be said.
Okay.
Yeah.
Yeah, thank you.
Great. Any other questions? Good.
If I may, sorry.
Yes,
Can I ask a question, Mukund?
Yes, of course.
This interesting factorization and the independence on sigma, as you said, it's not clear from the holographic CFT if there is an interpretation, but what about the auxiliary CFT? Is there anything interesting about this particular CFT2 block and the particular value of sigma that leads to this factorization, or is it just an accident?
Well, actually, it's more than it's. I don't know, but the statement is actually very, very interesting for the following reason. In 4 dimensions, as you well know, ADS5, this is a 4-point block because there are only 4 singularities. But my statement wasn't restricted for space-time dimensions.
So
Okay.
you could have multiple sigmas because then you have this COM channel and.
Yes, but the sigma that's really important is the one that is related to the monodromy between the horizon and infinity. There'll be other sigmas in the other channels, but they are not computing this monodromy. The monodromy, this cycle only knows about what's flowing out of it.
But do the other sigmas do not contribute to the evaluation of the formula of the 2-point function?
They're buried in the block. They're buried in the
But,
block. They're not in the gamma function.
But they do exist. But
They do exist.
Just
they just factorize. I think the whole set of all these other sigmas, everything else, that whole thing has to fall out as the simple polynomial. It's a remarkable statement about 2D CFT blocks, higher point blocks. So this is a corollary of this statement, but I don't know how to. I haven't tried proving it.
Do you know if this is a space of the COM channel? What happens if you consider some other?
I think it doesn't matter because all I'm really using is locality of the fusion.
Oh, yeah.
And so you could use anything as long as I'm allowed to fuse the horizon and the boundary first. I mean, maybe for historical accuracy, I should say that the formula by the Trieste group was primarily written not in this channel that I showed you, but it was written in a different channel where the boundary was fused with the singularity, with some other singular point. So what I would naturally call the T channel. And so their formula is useful for other purposes, but for the purpose of extracting the simplest monodromy, this channel is the nicest.
It's
great. So we basically sort of worked our way to the following statement that if we can control the asymptotics of cosine 2 pi sigma, if I can tell you how it behaves at high frequencies, then we are in business and we can say what the non-perturbative spectral function looks like. Okay, so I will tell you the answer, and in the next 5 minutes, I'll give you a sketch of how that computation was done. So here the keyword is manageable with exact WKB techniques. And let me just flash the answer first. The claim, this is now okay. For the sake of this discussion, for giving a full formula, I will restrict to D equals 4. We now have results for general D. it can be extended, but let me not do that. So cosine 2 pi sigma, I claim, has a full transseries expression, which is given by cosine pi nu. This is boring. There's some polynomial. These are perturbative corrections on top of some instanton. And the instanton action is 2v minus pi times w plus subleading instantons. Okay. I'll say this is some polynomial. And then just to indicate what the and v is some very simple function. And I haven't told you one other limit I have taken, so let me do that first. So v is some ratio of hypergeometrics and gamma functions. It's some number. And I've introduced this parameter zeta, which is momentum over frequency, or Q over W, same thing. And I'm taking omega to infinity, K to infinity, keeping zeta between 0 and 1. In other words, I'm trying to go to high frequencies, but at non-zero spatial momentum, while keeping that spatial momentum purely timelike. Okay, the story is slightly different. At purely zero momentum, the story is slightly different at purely null momentum, and the story is yet different for purely space-like momentum. Okay, so in this regime, this formula is the exact transseries. The detailed formula can be found in the paper. And from here, you can do two things, which I'll first say, and then say how we got this given the clock running down. From here, you can basically show that the spectral function, the non-perturbative part of the spectral function, which is now a function of omega and zeta omega, it basically is 1 plus some exact series steps of 2. Let me just write it as a polynomial of omega, and then the real part of. Okay. So that's the formula. So that's the result of the spectral function. And you see that it basically gives you the OPE answer with the 1, but then there are exponentially small corrections that we can pick up, and they very much depend on this parameter nu, V, that I introduced here. Okay, the ratio of the momentum to frequency. The trick for this computation was to basically compute the monodromy. And I think in light of time, I won't say much about WKB. the monodromy was computed by basically drawing the Stokes domains, figuring out which solutions were dominant and subdominant in different regions of the complex Z-plane, and asking how, as you cross one domain to the other, how the dominant solution mixes with the subdominant solution. That's really what we would do if you're doing classical with standard WKB. You have pre-propagation in the classical allowed region. You have exponential and growing and damped solutions in the classically forbidden region, and they will mix with each other as you sort of go from one region to the other. This is all controlled by the Stokes matrices. And the non-trivial aspect of this is that you basically can't just do the leading WKB, but if you wanted to get the full transseries, you have to resum that the Borel resum the perturbative expansion, pick up the directions in which you get the Borel resum converges. Okay, so that's in a nutshell what needs to be done. I will make a simpler comment though, which is related to my generalization, namely, if you wanted to pick up the leading WKB piece, okay, you don't want the full transseries, but you want to know what the leading correction is. It's sufficient for that to do a very elementary WKB analysis. You don't have to do the full-blown thing to get that piece. Okay? And that seems to work very well in general example. Okay, so now that I have this, what can I do with it? And what I can do with it is the following. I can use the following fact. So in the last 5 minutes, I'll say something about the black hole singularity. Let's look at the thermophile double correlator. Which is related to the spectral function by dividing out by this sine hyperbolic beta omega. So if I have the transseries for the spectral function, I have the transseries for the thermophile double correlator, and I can take my expression, which I won't write out, and consider the following object. I can Fourier transform back to time domain. And consider the function indexed by zeta as a function of time. Okay. Now, some basic facts about this object. First, let me say something about CTX in general and then specialize. So this is the complex T-plane. If you keep X fixed, then this correlator is analytic in this tip of with beta over 2. Okay, now zip of with beta. And it has cuts starting at the light cone. Okay. But of course, you have an analytic function in some domain which has cuts on some edges, but you can periodically continue it outside this domain by going around the cuts. If you're at finite momentum, then you're sampling all x's, and the cut extends all over the edge. Okay. So the smeared correlator will have an issue in because of the cut running all across the. So of course, if it was a fixed x correlator, the function is guaranteed to be analytic everywhere else. When I periodic text take it from the fundamental thermal domain and extend it. But now I can have singularities elsewhere. Okay. So if you take my expression for the spectral function, just divided by this sine hyperbolic, compute the Fourier transform, you will find that our spectral function has singularities in the complex time plane, the thermophilie double correlator, at the following loci. And then here R is integer which is greater than 1, S is. So you get a whole lattice of singularities, but they're all outside the fundamental domain. And the leading such singularity is can be identified with the singularity coming from the presence of the black hole singularity. So the identification as of we wrote the paper was tangential. In the limit, zeta goes to 0, V goes to 0, and the location of these singularities with what would be computed by bouncing null GD6 in the ADS black hole background. Okay, so this was the old calculation of FHKS, where they basically said, here's your black hole, here's the Penrose diagram. Singularity bends down. And space like GD6 connecting the two sides, should the thermophile double correlator be computable in the geodesic approximation, do something like this. And they're enveloped by a bouncing geodesic, which determines a critical time TC. Okay. And that TC can be read off from this formula. Okay. So the story can be improved a bit more. I think we have a story that's slightly nicer at non-zero zeta. In fact, I would make the argument that the zeta equals 0 limit is somewhat tricky, both from WKB point of view and from point of view of identifying what is actually dominating the WKB trajectories. But that is a story that I will be happy to say either in private or some other time. I think broadly what I wanted to convey was three statements. The fact that the spectral function is a nice object, and in particular that it factorizes at integer dimensions into a perturbative piece and non-perturbative piece. Second, the non-perturbative piece, at least in the holographic context, is completely under control, because as long as you can keep it under control using this exact WKB technology. And finally, once you have both those pieces together, you can say something about black hole singularities and where they're encoded in the high frequency behavior of the thermal spectral function. So the instanton contributions to thermal spectral function, the weights of those instantons are intimately tied with this bouncing geodesic time, the location of the singularities in the complex time. Those will be the three lessons that I will convey. So let me stop there.